Okay, next section is 2.3. We've already talked about polynomial functions, but we haven't really studied the ones with larger degrees, like 3, 4, 5th degree polynomials a whole lot. So we're going to focus on that on this section. So you'll learn about, we'll go back to graphs of polynomial function, we'll look at end behavior, some of the zeros, the intermediate value theorem, which you don't necessarily need to know the name, and we'll do some modeling again, some real world examples. Okay, so here's our polynomial functions again. I know I've given you this before, but you know, here's standard form for a polynomial function. Some vocab. Each of these is called a term. When it's in standard form, you have decreasing exponents, and the numbers in front are called coefficients. And the very first term is called a leading term. All right, so here is then an example of how we can shift this. So it's basically saying if the parent function is f of x equals ax to the fourth power, this is the fourth degree, how is this one shifted in comparison to this? Okay, so the first thing is this negative sign is a reflection over the x-axis. So it's reflected over x-axis. It's also shifted 2 units to the right. If you subtract 2 from x, that's horizontal shift. 2 units right. And then it's also shifted 5 units up because of that. And that's all in the formula sheet, in case you have forgotten. Okay, so cubic functions look like this. They're odd, right? And they have this general shape. They can have, you know, more of an elongated, I guess, relative maximum and minimum, like this one. And they can have up to, if you put an axis on here, they can have up to 3 real zeros. So if you change a to negative, the value in front of x, the leading coefficient, they flip over the x-axis, and then they would have this shape. Fourth degree is basically kind of like a parabola, but more of a U shape. And they can have some variations in there, have up to 4 real zeros if they cross the x-axis in the right spots. And then if a is negative, the coefficient on the leading term, then it reflects over the x-axis, as we know, in which case they'll open down. Okay, so then just a couple more things. Local extrema is what the book calls these. You know, if a polynomial of n degree has at most n minus 1 local extrema and at most n zeros, so like for an example, if you have a third degree polynomial like this, it's third degree, so it can have at most 3 real zeros, and then it's got n minus 1 local extreme points, so that'd be 1 relative maximum and 1 relative minimum, which is 2. N minus 1 is 2 in this case. Okay. This leading term test is not really that important. I'll just show you an example of what you need to know from that. Here's an example. Basically, what this means is if you have a fourth degree polynomial, we know this looks something like this. If the lead term is positive, then what that means is the limit as x approaches infinity of the function, which in this case is g of x, equals infinity. So what this means is as you go to the right, the function goes up. Okay? So at the limit of the function as x gets big, so as you go to the right, the function goes to positive infinity. That's what this means. And it's describing the end behavior that we're doing right now. So the other one is the limit as x gets small. So as x goes to the left, this function also goes to positive infinity. So I would write the same thing. G of x goes to infinity. That's describing the end behavior with the language of limits. And that's using the leading coefficient test to be able to know if this thing opens up and it's the general shape of U upward. So we can describe the end behavior from there. Okay. Finding zeros of a polynomial function is something we're going to want to do. So for this one, we can factor out a 2x. And that leaves me with x squared minus 2x minus 3. And then we can try to factor this some more into 2 linear factors. So factor this quadratic. We have x minus 3 and x plus 1. And then we can get our zeros from there. We have x equals 0 is a 0, as well as 3, and also negative 1. So we have 3 zeros from this function algebraically. From there, we know what this thing looks like. It goes through negative 1, goes through 0, and it goes through 3. So this thing must look like this. It's an odd function, so it starts down from the left and then goes up. Okay? Multiplicity actually matters as well. And this is what the book says about it. It says that the number up front here on the term is the multiplicity. So, and it also describes what happens to a function based on that multiplicity. So let me just explain that with this one here. What it means is this. We know this one has a 0 at -2, and it also has a 0 at 1. Okay? So if it's an odd multiplicity, then what that means is the function changes signs at that value. Okay? So an odd multiplicity, and that's what the paragraph above says, the function changes y value from positive to negative, or from negative to positive. Oh, my penmanship's a little bad. That's basically what this says here. Okay, and then if it's even multiplicity, this is all for multiplicity. In even multiplicity, like this one here, at 1, the function doesn't change signs. Okay? So we're talking about the sign of the y value. This one goes from negative to positive, and the y value here stays positive on an even multiplicity. So the function does not change signs. And we're talking about, when we talk about the sign, we're talking about the y value. It goes from negative to positive, and it stays positive at this one. All right. The other thing is the intermediate value theorem, which you don't need to know the name of this. All you need to know basically is that if we have a point here, we plug it in, we get a negative y value, and then we plug in a point that's larger than that first point, and we get a positive y value, that means the function must have changed signs somewhere in here, and there must be a 0. Okay? That's all that means. I think you might use the intermediate value theorem again in calculus, but for now, you don't need to know the name of it. We just need to use the common sense to know that if one point is negative, we plug in a larger x value, we get a point that's positive. The function obviously changed signs and therefore crossed the x-axis. All right? I hope this helps.